Welcome to the Daily Globe. Please subscribe and hit the bell icon for more breaking updates. For millennia, humanity has watched new stars flare and fade. Supernovae, the spectacular deaths of massive stars. These cosmic explosions forge the elements that make up planets and life itself. We are, quite literally, stardust. Today, October 14, 2025, marks a turning point in our quest to understand these cataclysms. The James Webb Space Telescope has captured, for the first time, the final moments of a massive star, before and after its explosive end. This isn't just another supernova. SN 2025 PHT is a breakthrough, unraveling a mystery that's puzzled astronomers for decades. For years, the likely progenitors of supernovae seem to vanish before exploding. Now Webb's infrared vision has found the missing stars, hidden behind thick veils of dust. This discovery forces us to rethink how the most massive stars live and die, and validates Webb's mission to see the unseen. Every new image is a testament to human curiosity, pushing the boundaries of what we know. The cosmos is full of wonders, and with each leap in technology, we illuminate a little more of the darkness. Supernovae have fascinated humanity since ancient times, their sudden brilliance recorded as omens and mysteries. Only in the last century did we learn these are not new stars, but the violent deaths of massive ones. A star more than 8 times the sun's mass lives fast, swells into a red supergiant, and collapses in a flash, triggering a supernova that seeds the cosmos with heavy elements. Yet, catching these events is a challenge. Supernovae are rare, unpredictable, and often hidden by cosmic dust. Astronomers scan thousands of galaxies, waiting for a single star to explode. Dust clouds, especially in star-forming regions, obscure many supernovae from view, making our census incomplete. We've long suspected that countless explosions go unseen, their light smothered by the very material they helped create. The universe's dusty veil has left us missing a crucial piece of the puzzle. Our understanding of stellar death has always been limited by what we can actually see, but now that's beginning to change. As our models improved, a mystery emerged: the red supergiant problem. Type 2 supernovae should come from red supergiants, giant stars, 8 to 25 times the sun's mass. Yet when astronomers checked pre-explosion images, the expected red supergiants were often missing. Was our theory wrong, or were these stars simply hidden? One idea stood out: red supergiants might cloak themselves in thick dust, making them invisible to optical telescopes. Their slow, dense winds could form an opaque shell, absorbing visible light but glowing in infrared. Until recently, we lacked the tools to see through this dust. The red supergiant problem persisted, a gap in our cosmic story. Were these stars evolving differently or just hiding in plain sight? The answer required a new way of seeing the universe. Enter the James Webb Space Telescope. In June 2025, astronomers spotted a brilliant new light in galaxy NGC 1637, SN 2025 PHT, a Type 2 supernova. Crucially, this galaxy had already been imaged by the James Webb Space Telescope. As the supernova faded, astronomers compared new and archival Webb data, pinpointing the explosion's exact location. There, in the pre-explosion infrared images, was a faint but distinct source, completely invisible in visible light. The missing progenitor had been found, hidden by dust. This was the breakthrough, Awad. A definitive before and after portrait of a dust-enshrouded red supergiant. For the first time, astronomers could say exactly what kind of star exploded. The evidence was clear. The red supergiant problem was not a flaw in our theories, but in our ability to see through dust. Webb's infrared vision had revealed what optical telescopes could not. The discovery electrified the astronomical community. It proved that many massive stars die shrouded in their own dust, invisible until now. The cosmic mystery was finally solved, not by new theory, but by new technology. A new era of supernova discovery had begun. The star behind SN 2025 PHT was no ordinary red supergiant. It was a true monster, 100,000 times brighter than our sun. Yet, in visible light, it was a ghost, its brilliance suffocated by a dense cocoon of dust. This dust, ejected in the star's final years, blocked almost all visible light, but glowed in infrared, making the star shine for Webb. The discovery confirmed that some red supergiants undergo intense mass loss, becoming heavily enshrouded before exploding. SN 2025 PHT's progenitor was the reddest and dustiest ever confirmed. Its light, skewed to red wavelengths, was a clear signature of its dusty shroud. This finding reveals that the final phase of a massive star's life is far more dramatic than we thought. Instead of quietly, waiting for collapse. These stars shed their outer layers, preparing their own cosmic shroud. Webb's data allowed astronomers to analyze the star's properties and the dust around it in unprecedented detail. For the first time, we have a high-resolution portrait of a doomed, dust-cloaked giant. The story of SN 2025P's progenitor could only be told with the James Webb Space Telescope. Unlike Hubble, which sees mostly visible light, Webb's infrared eyes pierce cosmic dust, revealing what was once hidden. It's like switching from headlights in fog to infrared goggles. Suddenly, the invisible becomes clear. Webb lets us peer into dusty star nurseries, galactic centers, and the cocoons of dying stars. In the case of SN 2025P, the star was a phantom in Hubble's images, but a beacon in Webb's. This ability is transforming astronomy, from studying the first galaxies to searching for habitable planets. The red supergiant problem wasn't a flaw in theory, but in our vision. Webb has given us new eyes, revealing a universe of hidden heat and shrouded light. The cosmos is richer and more complex than we ever imagined, and we're only just beginning to see it. Confirming that dust-enshrouded red supergiants explode changes our understanding of stellar evolution. The final stages of massive stars are more chaotic than we thought. Some shed huge amounts of mass, creating their own dusty shrouds. This superwind phase means stars may lose much of their mass before exploding, affecting the brightness and remnants of the supernova. Now with Webb's data, we can measure this mass loss directly. This helps explain the diversity of supernovae and their remnants. Some stars that should form black holes might instead become neutron stars. The discovery unifies different types of stellar explosions, showing how a star's life sets the stage for its death. By measuring pre-explosion mass loss, we can better predict the fate of massive stars. Webb is giving us the tools to rewrite the final chapters of stellar evolution. The cosmic story is more dynamic and interconnected than ever, and we're finally seeing it unfold in real time. The impact of SN 2025P's discovery goes far beyond stellar evolution. The dust from dying stars seeds new generations of stars and planets, enriching galaxies with the elements for life. Understanding dust production helps us model how galaxies evolve and how life's building blocks spread across the cosmos. The very dust that hid SN 2025P's progenitor will one day form new worlds. This breakthrough also affects cosmology. If many supernovae are hidden by dust, our measurements of the universe's expansion could be off. The solution came from combining Webb's infrared vision with decades of optical data from Hubble. Each wavelength reveals a different piece of the puzzle. Only together do we see the full picture. The story of SN 2025P is a testament to the power of collaboration and multi-wavelength astronomy. It reminds us that the universe is more interconnected than we ever imagined. And every discovery ripples outward, changing how we see the cosmos. The discovery of SN 2025P's hidden progenitor is just the beginning. With Webb, astronomers can now systematically hunt for dust-enshrouded stars across many galaxies. What was once a rare find will soon become a new field of study. We're moving from passive observers to proactive cosmic detectives, ready to catch stars in the act of dying. Webb's success shows the power of pushing technological boundaries. Each leap reveals new mysteries. The elements forged in dying stars will one day become new stars, planets, and perhaps life. The universe is in constant rebirth, and we are part of that cycle. Webb has solved a mystery, but opened a new realm of questions. Our journey into the infrared cosmos has just begun. The universe is waiting, and we're ready to explore.